So, welcome back to the class. So, today we'll start unit number 3, that is root locus and stability. So, here, before going to root locus, we'll discuss. So far, in unit number 1 and unit number 2, what you have done is you have found out the transfer function of the system. So, in unit number 1, you have formed the mathematical model, and taking a Laplace transform, you have found out the ratio of output to input, and that is called as transfer function. And then in unit number 2, initially you have modified that transfer function. That means any complex transfer function is simplified by using either a block diagram or by signal flow graph. So a complex transfer function is simplified. Then afterwards, in time response analysis, you found out the response of the system. That is, when you supply a transfer function with the known input like step, ramp or impulse input, how the output will vary. That you have found out in time response analysis. Now, these remaining two units, that is unit number 3 and unit number 4, you are going to perform stability. That is, you are going to check whether the system is stable or unstable. In unit number 3, by root locus technique as well as by Raoult stability criteria, you are going to check the stability in time domain. And whereas in unit number 4, by using the Nyquist plot or Bode plot, you are going to determine the stability in frequency domain. So in time response analysis, we have plotted the graph versus time. In frequency response analysis, you are going to plot the graph with respect to frequency. So both are important, but the frequency response analysis is more common because of its simplicity. So here we'll see the stability in time domain first, because unless you understand the stability, you cannot perform any further analysis. So first, let us discuss what is meant by stability. So here you can see the contents of that. First part is system stability. Here we will discuss what is meant by stability. Then how to obtain the stability of the system by using Raoult stability criteria or Raoult-Hurwitz criteria, or by more detailed analysis can be conducted by using what is known as root locus technique. So here this whole unit deals with stability in time domain. So it is extension of time response analysis only. So here you can see what is meant by stable or unstable. See here, there are 3 sketches. You can see the first one is totally stable system. So even if you try to make it unstable, unless large amount of force is applied, it will stay into this position. So this is stable. Whereas this is sort of what is known as limitedly stable or conditionally stable. Here what will happen, if you apply a small force, it will start rotating or moving, but it will stay on the ground only. Whereas in the third case, it is unstable because it is resting on a point. Even a small amount of disturbance will make this cone to fall. So it is a crude way of explaining what is meant by stability. It is not the actual uh, uh, theoretical way. See, now you can see the time response analysis. In time response analysis, if you see the graph of a stable system, it starts somewhere and comes to back to 0. This is stable system. Here you can see the neutral system or limitedly stable system, which is more commonly called as limitedly stable system. Here what will happen is the whatever input is given, it will stay throughout that input only. Neither it will increase nor it will decrease. So it is said that it is partially stable or limitedly stable. Whereas unstable system, even though input is given this much only, it will go on increasing with the time. So this becomes a unstable system. So details of that we'll discuss in future slides. At present, just look at these sketches, see the nature of the sketches, and from that you try to understand what is meant by a stable, limitedly stable, or unstable system. So some experiment, this is a stable bridge is there. This is broken bridge, unstable bridge because of voice oscillations. If large, see this is a suspension bridge. This is a suspension bridge. If there are a lot of oscillations to that due to wind or a traffic, it may start oscillating and it will collapse. Then here you can see the definition. The stability of a control system is defined as ability of any system is to provide the bounded in output when bounded input is applied. Remember, bounded input when it is applied, it will remain out, it will give you the bounded output. That means, suppose for a system, if I give a step input is a bounded input because it always remains constant at particular value, say 1, 2, or 3. So it is a bounded input. So the output of the system should come within that bound only. It can be more than 1 or less than 1, whatever it may be, depending on system gain. But it should remain that only. Whereas in unstable system, the bounded out, even though the bounded input is given, the output goes on increasing continuously and it will go out of the bound or out of the confined area, which we call it as a bounded area. So this is first condition. That is, the first condition of stability is when the input is bounded, output should be bounded. This is the first condition of stability. If you give a bounded input to that, you should get bounded output. For the best way to check the bounded input is step input. You cannot apply ramp input. Reason is ramp input is not a bounded input because it is continuously going on increasing or decreasing with the time. It will never remain constant. So that is not a bounded input. So the bounded input is either step input or a impulse input, because impulse input also one fixed value it will go and it becomes 0, but it will not go continuously go on increasing with the time or decreasing with the time. So you can only think of two standard test signals now, that is step input or impulse input, not parabolic or ramp input. And sinusoidal input is not considered here. Reason is it is not a frequency response analysis. Here we are talking about a time response analysis. So in frequency response analysis, we use sinusoidal input. So these are the further details. You can go through them. See here, this is the impulse response of the system. This is the impulse response of the system. If you give the impulse input to that, impulse input is like a square like this or a rectangle like this. That means what happens? It suddenly increases to value and then it becomes suddenly 0. So the output of the system, you see, it suddenly increases to that value and gradually go on decreasing. So this signal is more suitable for stability analysis, because the second rule says, so the first rule we have seen, first rule is what? When the input is bounded, output should be bounded. So second rule says that in the absence of input, the system output should tend towards 0. It should come back to 0. So the impulse input is the best suited signal. Why? Because step input, what happens? It will never become 0. It will remain as a step only. A size of the step may be anything. So one, it is rises that to that level, it remains constant throughout. So it can be suited to check the first rule only. That is, if the input is bounded, output is bounded. Whereas the second rule, in the absence of input, output should tend to 0. Step input never becomes 0. it will always remain constant. So that is not suitable. Whereas both the rules can be tested by impulse signal only, because impulse input first rises to certain value like a step, and then it becomes 0. So in that case, both the rules can be checked by using the impulse input. So when the input is bounded, output remains within the bound or not, that you can check. At the same time, if the input is 0 or in the absence of the input, output should tend towards 0 or not. Here, this is a typical case of a system which is perfectly stable. Reason is, when it is applied with the impulse input, it first jumps to that value, and then when the impulse signal vanishes, then it slowly comes to 0. This is unstable signal. It is once again for the impulse input, it suddenly jumps to that value, but it goes on increasing like that further. So that means even though the input is bounded, output is not bounded. So the system is unstable. So this is an unstable system graph. So here you can see the general transfer function of the system can be expressed by y upon x, as where y is output and x is input. So it is nth order system. Nth order system can be written as b naught into s to the power m plus b1 into s to the power m minus 1 plus b2 into s to the power m minus 2, so on, bm minus 1 into s plus bm. So in the numerator, there are m terms are there. M terms are there. Whereas in the denominator, there are n terms. Generally, in all transfer function, the denominator order is greater than numerator order. So n here is greater than m. So in the denominator, you can see it is a naught into s to the power n plus a1 into s to the power n minus 1 plus a2 into s to the power n minus 2, so on up to an minus 1 into s plus an. So there are n terms in the denominator and m terms in the numerator. The condition is n should be greater than m. It can be same, but it cannot be greater. It can be equal to or greater than. That condition is always there, and most of the cases it is like that only. So here the same equation, it is written once again. So the denominator of the polynomial is greater than the numerator polynomial. This is the first condition. So this transfer function, when you expand, it will be in this form. It should not be bracketed. I multiply all the brackets in the numerator and multiply all the brackets in the denominator. So you will get only s to the power m, s to the power m minus 1, so on up to s to the power 0 in the numerator. Similarly, s to the power n, s to the power n minus 1, so on up to s to the power 0 in the denominator. Where b0, b1, b2, b3 up to bm are constants. Whereas similarly in the denominator, you have a0, a1, a2 up to an are the constants. So here you can proceed further. There are two things of stability. One is called as absolute stability. One is relative stability analysis. Both the analysis you can do here. So absolute stability means you are only interested in finding whether the system is absolutely stable or not stable. But relative stability means in relation with another system. That means if you have two systems, you want to check which system is more stable than the other one, or which system is less stable than the other one. That is called as relative stability analysis. Absolute stability analysis is just to find whether the system is stable or unstable. But once you find the absolute stability and you have system A and system B, out of A, suppose A and B both are stable system, I want to check whether A is more stable than B or B is more stable than A. As relative stability analysis. Okay. Now comes to what is known as poles and zero concept. Next we will come to poles and zero concept. In Raoult stability criteria, it is not important. but in root locus it is important. The pole is one which makes the system transfer function tend to infinity, whereas 0 is one which makes the system transfer function 0. For example, here suppose if I put a naught as 0, if I put a naught or 0 or a1 as 0 or a1 equal to 0 or a2 suppose if I put s to the power n is equal to 0, or actually it should be explained in the bracketed form. Suppose there is, if you have, this is not the correct way of explaining that. Suppose you have a terms called as in the numerator, suppose you have a term called as k, the transfer function is k into s plus a divided by s plus b into s plus c. There are three brackets total. One bracket is in numerator, that is k into s plus a. A is in the numerator. Similarly, in the denominator, suppose you have s plus b and s plus c. Two brackets are there. Suppose if I put s plus b, there is a denominator term s plus b, that is s is equal to minus b. If I put s is equal to minus b, then s plus b becomes 0. So that means anything in the denominator gets multiplied by 0 means that is when the denominator becomes 0, the transfer function becomes infinity. So that means I will say there is one pole at s is equal to b. At s is equal to minus b, there is one pole. Similarly, at s is equal to minus c also there is another pole. So the poles are in the denominator and zeros are in the numerator indirectly. So similarly, there is in the numerator, I said k multiplied by s plus a term is there. If I put s is equal to minus a, if I put s is equal to minus a, then s plus a, s value is minus a. If I put, then that bracket becomes 0. So k multiplied by 0 becomes, the transfer function becomes 0. That means there is one 0 in the system. So this is the way to find out the number of poles and number of zeros. So you see here, there are n poles and m zeros here. So because there are m terms in the numerator, n terms in the denominator. So there can be m values of s, which makes the transfer function 0, whereas there are n values of s, which makes the transfer function infinity. So if you put that, that means suppose if I put a naught equal to 0, whole thing becomes 0, like that. So consider this example. This is a transfer function x divided by y is equal to c into as plus b. Okay. Now in the numerator there is no s. When there is no s, you cannot put that equal to 0. So there is no 0 in the system. So number of zeros is 0. Whereas in the denominator, if you put as plus b equal to 0, so that means if you put s is equal to minus b by a, if you put s is equal to minus b by a, this will become 0. So when the denominator becomes 0, the transfer function becomes infinity. When the denominator becomes 0, c divided by 0 is infinity. So there is one pole here because the denominator corresponds to pole and numerator corresponds to 0. So there is one pole at minus b by a. This is what is the concept. So here you can see the complex plane is explained here. The complex plane here is represented by x-axis represent the real part, whereas y-axis represent the imaginary part. And this is in a Cartesian coordinates, not in a polar coordinate. For example, S is represented as sigma plus j omega, where sigma is the real part and omega is the imaginary part. So what you have to do to plot this point S in the graph, first you measure the real part, measure sigma on sigma axis, and then measure omega on omega axis. So point S may be lying here if both are positive. If both are positive, point will lie here, whereas this is the real part, which is sigma, and this is imaginary part, which is omega. If this is sigma minus j omega is there, sigma is on the positive real axis, whereas omega is in the negative real axis. Point will lie here. That is in the second quadrant. If both are negative, minus sigma minus j omega, then it will come in the third quadrant. If the imaginary part is positive and real part is negative, that is sigma is negative and omega is positive, it will come in the fourth quadrant. So remember here it is in the Cartesian coordinate. Cartesian coordinate, how you draw the graph? First you measure x coordinate and then y coordinate. Here our x coordinate is real coordinate and y coordinate is imaginary coordinate along with the sign. So both are plotted separately. So it is in the Cartesian coordinate system. Now here we'll go to this graph. See the stability of impulse response. Suppose in S is here. S is here means what? It has zero imaginary part because omega is 0, whereas some minus real part because it is on the what is known as in the second quadrant. In this it is in the fourth quadrant. It is in the fourth quadrant. In the fourth quadrant, real part is negative, imaginary part is positive or 0. So it is here on negative real axis. If that means there is only one pole here. Only one pole means highest power of S in the denominator is 1. So highest power of S in the denominator is 1 and in the numerator there is nothing. That means there is only one pole. And that pole also has negative real part. If you see the impulse response of that, what is happening is it is like a perfect stable system. That means it is following both the conditions of the stability. That is, when the input is bounded, output is bounded, and in the absence of input, output tends to 0. So I am applying an impulse signal to this. That means one square wave I am applying to that. So when the square suddenly jumps to this value, it starts from this value. And when the square vanishes, then this gradually tending to 0. So this is the example of our stable system. In the previous slide, I have shown it. But the same first order system has one pole on the right side. So the pole is represented by a cross mark. There is an X mark here you can see. That means this pole, that is the denominator pole, has a positive real part. That means that is S minus A is equal to 0. That is S is equal to plus A. So it has a positive real part. If it has a positive real part, see the output. See the output of the system. It is starting here and gradually going on increasing for infinity. So this is the typical case of unstable system. So from that, what we can understand is if a pole has a negative real part, the system is stable. If the pole has positive real part, the system is unstable. Or indirectly, we can say if the roots of the system have positive real part, it is unstable. If the roots of the system has negative real part, the system is stable. Now let us go for two poles which are complex conjugate. That means it has negative real part and positive imaginary part and negative imaginary part. So there are two poles here. Both poles have same real part, whereas They have same imaginary part, but one side it is one positive, one negative. That is minus sigma plus j omega minus sigma minus j omega. So there are two poles. If you see the impulse response of that, it is oscillatory. But see, these oscillations are continuously dying down and approaching zero. But if you see the another complex conjugate pole, here it is plus sigma plus j omega and minus j omega. That means it has plus real part and positive or negative imaginary part. In that case, see the output of the system for the impulse response. It is continuously going on increasing. That means it is unstable. So that clearly says that imaginary part doesn't play any important role at all. But the real part plays the important role. If the system has negative real, if the roots of the system has negative real part, the system is stable. If the roots of the system has positive real part, system is unstable. Here also same thing has happened. If the system here has negative real part, the system is stable. The system here has positive real part, the system is unstable. Only difference between the response is here the roots are on real axis in these cases. So the response is non-oscillatory. Whereas here the roots have both real and imaginary parts, the response is oscillatory. So take the case of our second order underdamped system. It has two poles which has both real and imaginary part. So the real part is sigma, imaginary part is j omega. So if it is underdamped system, the response is oscillatory. If it is overdamped and critically damped system, response is non-oscillatory. Similarly, other two cases. See now here the third case, which is extension of this. This is the extension of this sketch. If it has zero real part, that is on the imaginary axis only the poles lie. That is one with positive j omega, 0 plus j omega, 0 minus j omega. The response you can see here. What does it indicate? What does it indicate? So if the input is bounded, output is bounded. It will remain in the bond only. But in the absence of input, the output doesn't tend to zero. It will keep on oscillating forever. So that means the system is neither stable nor unstable. In that case, it is called as limitedly or conditionally stable because it follows the first law. First law of stability, if the input is bounded, output is bounded. So when the input is bounded, output remains within the bound. But in the absence of input, output should tend to zero. It is not tending to zero. So it is following the first condition of stability, but it is not following the second condition of stability. So neither this system is stable nor totally unstable. In that case, it is called as limitedly stable. Now your criteria is limitedly stable system is also unstable only. We don't require that. So if you want to classify the system into only two categories, stable and unstable, then limitedly stable system also comes under unstable system only category. But if you have three, if your idea is broader, that means if you have three categories, stable, limitedly stable, unstable, then this comes under second category, that is limitedly stable. If there are multiple roots on the j omega axis at the same point, there are two roots here, two roots here. So this is a fourth order system because the highest power of s is 4 because there are 4 roots. So 2 here, 2 here. At the same point there are 2. Then also the system is not limitedly stable but unstable. Same thing of this case. If suppose if the root is at the origin, that means it has 0 real part and 0 imaginary part. The system becomes limitedly stable. That is bounded input, output is bounded, but in the absence of input, output is not coming towards 0. It follows the first law but doesn't follow the second law of the stability. If there are multiple roots at the origin, a square term is there. Sometimes only a square is there. A square term means there are two roots at origin only. So when there are two roots at origin, the output is continuously increasing with the time. So it is unstable. So indirectly, what does it mean? That if you plot the real imaginary graph, this is the real axis, sigma and j omega graph. If the roots are on the right side of the j omega axis, the system is unstable. If the roots are falling in this region, that is in quadrant number 1 and quadrant number 2, the system is unstable. Whereas if the roots are falling on the left hand side of the j omega axis, that is in quadrant number 3 and quadrant number 4, the system is stable. This is what it says. This is regarding the stability part. That means it has to follow the two rules. First rule is if the input is bounded, output should remain bounded. The second rule is in the absence of input, or if the input is 0, output should also become 0 or tend towards 0. It may take long time, but it should tend towards 0. So these are the two rules of the stability, and basis of that we have found out that if the roots have a positive real part, sorry, I skipped it. If the roots have positive real part, that means they are in quadrant number 1 and 2, the system is unstable. If the roots have negative real part, the system is stable. But if their roots have zero real part, that means on the j omega axis they are falling, and there are no non-repeated roots are there. When there are no non-repeated roots, then system is limitedly stable. But if on zero real part with repeated roots at the same point, the system is once again unstable. That means what you have to do is, that means once you find out the characteristic equation, that is 1 plus g of s h of s is equal to 0, which we have seen earlier. If you in time response analysis also we have discussed about what is known as characteristic equation. Characteristic equation is written as q of s, which is equal to 1 plus g of s h of s equated to 0. If the roots of the characteristic equation has all the roots of the equation have negative real part, then the system is stable. If the roots have positive real part, at least one, if it has a positive real part, then the system is unstable. If all have positive real part with one zero real part, then the system is limitedly stable. That means if all the roots, suppose it is nth order system means it has n roots. If all n roots have negative real part, then the system is stable. If all or any one, not necessarily all, out of n roots, even one has positive real part, system becomes unstable. This is what is the condition. Now that means we have to indirectly find out the roots of the characteristic equation. So to find out the roots of the characteristic equation, see, first order system is there, only one root you can easily find. Second order equation is there. Second order equation is that is as square plus bs plus c is the second order equation. Highest power of s is 2. The roots can be easily found out by the method minus b plus or minus b square minus under root of b square minus 4ac divided by 2a formula. So you can find out. But if the equation is third order, you have to do some trial and error method or try to solve the cubic equation. So your calculator may be able to solve the cubic equation. You can find the roots of the cubic equation. But suppose if it is fourth order, fifth order, sixth order, seventh order, or nth order equation, how to find out the roots? That is practically very difficult, or not practically, it is impossible. Without computer, you cannot find out. And this theory is developed before the development of computer. Remember, this theory is somewhere developed in 1960s. So that time there were no computers, and even though computers were there, they were very expensive, which cannot be in the reach of the people. Only some high-end scientific labs used to have a computer even in 1970s also. So finding out, and those computers also have a very limited capacity. The processor was very weak. So it used to take, if you give the one sixth order or seventh order equation to solve to that computer, it may used to take days together to get the answer, not minutes. Now you are very much within fraction of a second you get the answer. But in those days, it used to take days together. One simple, for example, if I give, suppose you have a problem like in ANSYS, you have a problem like plate with a hole, which you do it as a first exercise in your lab. To solve that equation, computer used to take 1 day or so. CDC Cyber, which was there in IIT Delhi and IIT Bombay, used to take one simple fourth order, fifth order equation to solve that. It used to take 8 hours, 7 hours like that. So in those days, it was practically difficult. So they have some mathematicians like Hurwitz and Roths. They have developed a criteria without actually finding out the roots. They have found out the way whether they have a positive real part or negative real part. That is what is the Routh stability criteria. In the next class, we can go with that. Have you understood this? What is meant by stability?
Yes, sir.
Yes. Okay. So both the rules are very important. Remember both the rules. When the input is bounded, output should be bounded, and in the absence of input, output should tend to zero. These two rules have to follow. And at the same time, you have concluded that if the roots have negative real part, the system is stable. If the roots have positive real part, the system is unstable. If the roots have zero real part, then the system is limitedly stable. If the roots are falling on the left hand side, the system stable. Roots are falling on the right hand side, the system is unstable. If they are falling on the line y-axis or j omega axis, and if they are non-repeated at the same spot, there should not be more than one, then the system is limitedly stable. Practically, limitedly stable also categorized as unstable system only. But further analysis you can find out can it is whether it is limitedly stable or unstable. So here we'll stop today. In the next class, we'll start with the Routh stability.